Welcome to this video recording on the lesson on the principle of duality. This is part of the syllabus DC circuit analysis for semester 3 of the BSc program under the chapter under the syllabus Physics 301 Electricity and Magnetism. So in this session we are going to look at the principle of duality, give examples for duals, and also we will be looking at the use of the principle of duality to show that voltage and current sources are duals of each other, and also we will see how using this idea a voltage source can be converted into an equivalent current source. This is the program for this session. Now, in electronics, we come across several pairs of quantities which are often spoken of as duals. The quantities are current and voltage as far as quantities are concerned, resistances in parallel, resistances in series, or in other words parallel and series combinations as in circuits. Again, as far as certain other quantities are concerned, we can speak of resistance and conductance, reactance and susceptance, and also impedance and admittance. And again, as far as circuits are concerned, we can speak of short circuit and open circuit as the duals of one another. Similarly, we also have the Kirchhoff law, that is Kirchhoff's current law, being a dual of the Kirchhoff's voltage law. Then we also can speak of the Thevenin's theorem and the Norton's theorem as duals. When we talk of duals, it is also true that mathematical forms of some physical relations are also can be spoken of as duals. For example, if we have two resistors R1 R2 connected across a source of EMF V, and the voltage drops across the resistors are V1 and V2, these voltage drops can be written as V1 is equal to V into R1 R2 by R1 plus R2, and similarly V2 is equal to R2 by R1 plus R2 into the source voltage V, and the dual of this relationship will be the current division formula. For two resistances connected in parallel, this will be I1 is equal to I into G1 by G1 plus G2, and I2 is equal to I into G2 by G1 plus G2. We have to be careful here. If we represent the branch currents as resistances, flowing in resistances, we would be writing them as main current into resistance of the other branch divided by sum of the resistances, which is usually the case with our representations. But here, when I am using conductances, we will be constrained to use the same conductance for the branch current. For example, when I talk of I1, I will talk of G1 together. So I1 G1 divided by G1 plus G2. Similarly, I2 G2 divided by G1 plus G2. That will be the formula for the branch current. Again, the voltage division formula and the current division formula are duals of each other. Similarly, we can think of quantities, pairs having an origin which is similar as the duals of one another. For example, electricity and magnetism as a whole. We know magnetic phenomena arise when current flowing through a conductor and current is flowing through a conductor. Currents flowing through conductors produce magnetic fields. Similarly, whenever the magnetic flux linked with a coil changes, we see that an EMF is induced in it. So, electrical phenomena give rise to magnetic phenomena, and magnetic phenomena give rise to electric phenomena. So, we can talk of electricity and magnetism as duals of each other. This duality can also be found in circuits. If two circuits are duals of each other, then the situation will be that the mesh equations for one will have the same form as the nodal equations of the other. Now, there is need for some explanation here because we will not be familiar with the idea of nodal equations. We are familiar with the Kirchhoff's voltage law representation of electric circuits, wherein we assume currents through each mesh and write out the KVL equations. Similarly, what we can do for any network is we assume currents in each branch and write out the equations in terms of KCL. For example, under KCL, we have at any node some of the currents coming in, some currents going out. We represent each such current as a voltage difference across the ends of the resistor divided by that value of resistance itself. When we do that, we will be writing out equations for the meshes in terms of voltage differences across components and corresponding resistances. What we do here is we identify the number of nodes in the network, assign voltages to each one of these nodes. One of the nodes we call as the reference node. Arbitrarily give a voltage 0 to it. Then at each node we write out the KCL equations in terms of the potential differences across the resistors, in terms of battery voltages and the voltages at the node and the corresponding resistances. Then what happens is the KVL equations will be having the same form as the equations based on KCL. The KVL equations we call them as mesh equations. The KCL equations we can call them as nodal equations. So the nodal equations and the mesh equation and the voltage equations will be, or the mesh equations will have the same form. It does not, therefore what does it mean? It means that the way in which voltage or current in one circuit behaves in the other circuit, or the dual of it, current and voltage will behave in the same manner. You please remember the order here, not the two voltages or not the two currents. Current and voltage in one behaves the same way as the voltage and current in the other. Further, why this happens is because, as I told you just now, the mesh equations are written in terms of the voltages and the nodal equations are written in terms of the currents, and current and voltage by themselves are duals. Two such, or in other words, such equations, the mesh equations and the nodal equations, they are called exact duals of each other when the mesh equations for one is numerically identical with the nodal equation for the other. Here I don't mean the currents and voltages will be same in both the representations, but the form of the equation, that will be identical. Two identical equations in terms of numbers. So with all the foregoing, and similarly we can also show that voltage sources and current sources are also duals of each other. Now, having spoken for this duration and taken several examples, what we can now say in conclusion is that when we talk of duals, they have the same origin, but many a time they are complements of each other. As we kept referring to, the conductance is the reciprocal of resistance. What resistance does in a circuit, the conductance just does the opposite. Please remember, resistance represents the opposition to the flow of current in a circuit. conductance represents the ease with which currents can be set up in a circuit through resistors. So they are representing the opposite fact or complementary fact. But the physical reality they are representing is the same. This is simply two different ways of looking at the same issue. Two complementary ways of looking at the same issue. Now, what is the further use of a principle like this? The further use of a principle like this we will be making use of in showing that a current source and a voltage source are equivalent to each other. They are the duals of each other, and a given current source can be converted into an equivalent voltage source. The discussion is slightly involved, so I would require you to pay good attention to what I am going to say. Requires definitely a good lot of attention and keeping in mind as you go on listening to what I have previously said. Now, I am given a source, a DC source, which provides me some EMF. I have connected a load across it. Now, how the source behaves is not known to me. The source can behave in two ways. It can behave like a voltage source. It can also behave like a current source. Now, when does it behave like a voltage source? When does it behave like a current source? This is the issue. We have seen, or we can see using Ohm's law, that a source of EMF or an energy source behaves like a voltage source when its internal resistance is small and the external resistance that we have connected across it is large. Similarly, the source will behave like a current source when its own internal resistance is very large compared to the load resistance. This we have seen in earlier sessions also. Now, I am given a voltage source, I am given an energy source. I will first treat it as an voltage source, having a output voltage of Vs, that's the source voltage. It will have an internal resistance which I have represented as Rs1. Now, if I represent the same source as a current source, then I will have a situation where I will have some source current supplied by the energy source, and that source current maximum that I have taken it as Is. The representation of a practical current source, as you are familiar with, is its internal resistance is taken parallel to the current source. So that internal resistance of the current source I have simply taken it as Rs2. The same RL is connected across the current source. Now, the two sources will be equivalent if the output voltage or the short circuit current, let me say. In short circuit, when we short circuit these two supplies, the short circuit current that flows through the voltage source should be the same as the short circuit current that the source can provide to the load. I will repeat. When we short the source, the load current that is flowing through the load resistance RL in the voltage source representation should be the same as the current that flows through the load resistance when the load is shorted. Secondly, when we come to the open source representation, in other words, we open circuit the voltage source as well as the current source, and when we do that, the voltage across the load terminals in the voltage source representation and current source representation should be the same voltage. Then the two sources are identical. We can then go ahead and say if the load resistance is finite, that is in between the two extreme limits that I am talking about, open and short, then I would have completely shown that the two sources are identical, and I would have also shown that I have converted a voltage source into an equivalent current source. So both the jobs, both the tasks would have been achieved. Now let me start. If I consider the voltage source to be having a source voltage Vs and internal resistance Rs1, and in the current source case, the maximum current or source current, I will call it as Is, its internal resistance as Rs2. Now, I will first short circuit the voltage source. If I short circuit the voltage source, if you go back to my circuit, the short circuit current flowing through the load would have been IL is equal to Vs divided by Rs1. In the voltage source representation, the internal resistance Rs and the load, they are in series. Load is shorted, so the only resistance in the circuit is Rs1, and that will limit the short circuit current that is flowing through the load resistance. Load resistance, of course, is not there. Therefore, that is equal to IL is equal to Vs divided by Rs1. Now, if I short circuit the load in the case of the current source, then the short circuit current which would have flown through the load, IL, that is equal to Is, the source current, because of the short, the entire current provided by the supply will not flow through the Rs2 but would have flown through the short now. And that current, of course, would have been limited by Rs2 according to the branch current formula. Now that current IL, which is Is equal to the voltage that would have appeared otherwise across the current source, which is Vs, because the two sources are identical. The same source being represented in two different ways. That's what I mean when I say identical. So the voltage source would have provided a voltage Vs2. The current is now IL, and that is equal to Vs divided by Rs2 if the same source is represented as a current source, where Rs2 is the internal resistance of the current source. Now, we now go to the other extreme. We open circuit the load terminals. When we open circuit the load terminals, the source voltage, if I call it as the terminal voltage Vt, that will become equal to source voltage Vs. In other case, what would have happened? An Ri would have been there, an RL would have been there. According to the voltage divider formula, the voltage of the source would have gotten divided. Now, the load is removed, therefore no current in the circuit, no voltage drop therefore across the internal resistance. Whatever is the source voltage, that would have come back at the output terminals. This is easy for you to see because of the Ohm's law that you have studied earlier. Now, that source voltage is Vs. So Vs is equal to, therefore, if I represent the same voltage by an Ohm's law relationship, would have been Vs is equal to IL into Rs1. Now for the current source, if you take, the load has been open circuited. The source is not giving any current to any load, but since it is open circuited, the voltage that would have appeared across the current source would be equal to Vs, because it's the same source being represented in a different way. So that Vs would have been equal to Is into Rs2, as we have seen earlier. For the voltage source, the same representation of Vs, we would take it as IL into Rs1 or Is into Rs1. Both are open circuited, so only voltages will be there. We are trying to represent them by means of their Ohm's law equivalents. Since the two voltages when open circuited, that is the voltage appearing across the load in the voltage source configuration and also in the current source configuration are the same, and that's equal to Vs, we have the situation, their Ohm's law representations providing us with the equations Is Rs1 is equal to Is into Rs2, which implies that Rs1 is equal to Rs2. When Rs1 is equal to Rs2, it is now clear that a voltage source can be converted into an equivalent current source by simply knowing what is the internal resistance of the source, and in the voltage series, if it's already a voltage source, you convert it into an equivalent current source by placing a resistance of the same value as the internal resistance of the cell parallel to the current source. In a similar way, if there is a current source whose internal resistance is Rs, put that Rs in series with the voltage source, you will get the equivalent voltage source. So, a current source can be converted into an equivalent voltage source by simply changing the positions of the resistances. The internal resistance you take, put it in series with the voltage source, ideal voltage source, you get the practical voltage source. The same internal resistance placed parallel to an ideal current source will give the equivalent practical current source. So this is how we convert current source into voltage source. If somebody asks you how is a voltage source converted into its current source equivalent, then you can come up to this stage and stop. Now we go further and see what happens. These two situations that we represented are the extreme situations, open and short circuits. Now, we have shown that in the extreme cases, the two sources behave equivalently, which means when we short both, the short circuit current through the load will be same in both the cases. When we open circuit them, the open circuit voltage across the two sources, the voltage and the current source will be same. Now, if the RL value, that is the resistance of the load, is anywhere between these two extremes, then what happens? In the voltage source representation, there will be a voltage drop across the internal resistance. In the current source representation, the maximum current that the source would have otherwise provided will now be divided across the internal resistance and the load resistance. So, when this happens, let us see how the source behaves. If RL is the load resistance and that is finite, in the voltage source representation, the current IL1 that flows through the source is equal to Vs divided by Rs plus RL. Because it's a voltage divider, Rs is the internal resistance of the source, RL is the load resistance. Here, when I said Rs1 is equal to Rs2, in the previous case, I have equated them to an Rs here. Now in the current source representation, it will be, if I call the load current as IL2 deliberately, then IL2 will be obtained by using the branch current formula, which is main current Is into resistance of the other branch, that is Rs, divided by sum of the resistances, that is Rs plus RL. But Is into Rs, the product, represents the source voltage Vs. Therefore, IL2 becomes Vs divided by Rs plus RL. So this leads us to a situation where the load resistance will draw the same current. IL1 therefore becomes equal to IL2, the same current from a given source, whether you represent it as a voltage source or you represent it as a current source. So, we have shown in the extreme cases of open and short that the output voltages in the case of open circuits and short circuit currents in the case of a short circuit for both the source representations will be same. Now, for any finite load, we are showing that the current drawn from the sources will be the same. Therefore, we have completely shown that the two sources are identical. So, this leads us to the conclusion, two major conclusions. One is that a given voltage source can be converted into an equivalent current source by placing the internal resistance of the source in parallel with the current source. Similarly, a voltage source is a dual of the current source. because the behaviors of the two sources will be the same under all circuit conditions. So with this, it brings us to the end of the session. Just to recap what we have done in the session, we discussed the principle of duality. The principle of duality, I will repeat the statement, is an idea that two quantities are complements of each other, and in a given circuit, in a given situation, whether it is writing the mathematical relationships or building circuits, in a given situation, if one of them is replaced by its dual, then the forms of the equations, the nature of the behavior of the circuit, etc. will be the same. I'll repeat again. Principle of duality is simply that in any physical situation, particularly we are talking of electric circuits here, in any electric circuit, if a given quantity is represented in various mathematical equations and physical situations, if one quantity is replaced by its dual, then the nature of the equations, the nature of the behavior of the circuit, etc. will not change. Then we have provided for this idea a large number of examples from circuits, from reciprocal quantities, from forms of mathematical equations, etc. Then we did using the principle an effort to show that a voltage source is the dual of a current source, and in the process we have also shown that a practical voltage source can be converted into a practical current source by simply knowing the internal resistance of the voltage source and putting the same in parallel with an ideal current source. So this brings us to the end of our session. Before we wind up, we look at suggestions for further reading. As I have been doing in this chapter, in this video series, I have taken usually 5 books for further studies and reference. One is the Electrical Networks by B.L. Teresa, 3rd revised edition. Then Introductory Circuit Analysis by R.L. Boylestad. Then there are several internet-based sources, anyone you can tap into. There are sites like Electronics for You, Circuit Globe, all about electronics, all about circuits, and every university has also put out course material, source material on all these topics. And further, if I have to suggest to you any one source, one textbook specifically written for the 3rd semester, then in this session I would suggest to you the book by Dr. Y.S. Vidya and Dr. H.C. Manjunatha. This is published by Sunstar Publications. Title is Smart Physics, Part 3, Electricity and Magnetism. Particularly, I have referred to this textbook in telling you about the voltage source and current source and their interconversion based on the duality theorem. Finally, Resnick and Halliday, Principles of Physics, 10th edition. This will be for not only this subject but also as a general physics reference book. Thank you very much.